Welcome to the Deep Dive. We're the show that digs through complex information to find those really fascinating nuggets, giving you a shortcut to understanding what matters. Today, we are plunging into a really exciting corner of material science. We're talking about amorphous chalcogenides, and specifically how scientists are now creating new 2D materials, atom-thin materials, with some genuinely surprising properties. Think of it as a journey maybe from theory almost to real-world game-changing stuff. For this dive, we're drawing on two key papers from Nature Materials. There's the main research article by Zudoshi and colleagues published June 23rd, 2025, and then a really helpful news and views perspective on that work by Volker L. Derringer, which came out just about a month later, July 30th, 2025.
Yeah, and what's so interesting here is the focus on amorphous materials. The word itself might sound a bit technical, but really just think of glass. Unlike a perfect crystal, like salt or diamond with atoms all lined up, amorphous materials, they lack that long-range order. The atoms are more, let's say, jumbled. But here's the twist these papers highlight. That jumble, that disorder. It isn't a mistake. It's actually a characteristic they can use. It's where the interesting properties emerge. This imperfection is kind of the point.
Okay, so disorder is good here.
In a way, yes. The potential is, well, it's quite significant because they don't have that perfect repeating structure.
Yeah.
They can have more sort of available atoms on the surface, atoms ready to react or interact differently. And that gives them unique electronic or catalytic properties compared to their crystalline cousins, properties that could lead to some real breakthroughs.
Right, so if this disorder is so promising, what's been the holdup? What was the big challenge, the roadblock that she and colleagues seem to have overcome now? Because getting these materials made reliably, super thin, like one atom thick, and crucially at a large enough scale for actual use. That's been tough, right?
Exactly. That's been the bottleneck, making them consistently wafer-scale thin.
Okay, so maybe let's unpack that historical difficulty a bit. Why has disorder been such a tricky thing to work with, especially in these thin materials? Derringer's piece actually points back, way back, to Zachariason's 1932 paper about glass structure.
Oh yeah, Zacharias, he had these simple drawings comparing a crystal, maybe a neat honeycomb pattern to an amorphous version, still connected locally the same way, but forming these disordered rings of different sizes. Just a concept back
And
then.
a concept from 1932.
Right, and then fast forward to almost 80 years to the early 2010s, scientists were imaging silica layers, glass basically,
Yeah.
and they saw those exact kinds of disordered rings Zachariason predicted, almost by accident, confirming his idea. It was quite remarkable.
Wow, so the idea was sound, but making them intentionally.
Well, beyond just confirming old theories, people started seeing practical potential in disorder. There were hints, like taking graphene, which is normally a great conductor, and deliberately damaging it, introducing defects, suddenly changed its electronic behavior. It could act more like a semiconductor, opening up a band gap.
So controlling the damage gave it new function.
Precisely. And there's another example with monolayer amorphous carbon, basically, graphene's messy sibling. By tuning how disordered it was, researchers could control its conductivity. Really useful for electronics.
Okay, so the potential was clearly there. People knew disorder could be useful.
But the big problem remained. How do you grow these things as large, perfectly flat, single layers? Especially for materials that don't naturally form layers. Materials whose bulk form isn't like graphite, not sheet-like.
Right, you can't just peel them off like graphene.
Exactly. They tend to clump up, form little 3D islands instead of spreading out flat. And for devices, you need that flat, continuous sheet.
Okay, so that sets the stage. And this is where it gets really interesting. This is the problem that Zudoshi and his colleagues tackled head-on in their Nature Materials paper.
Yes. And it's the solution that Volker Derringer highlighted as being so clever in his commentary. What Xi's team came up with is this really novel growth method. They call it a nanodroplet-driven nanoribbon-to-film strategy. It uses chemical vapor deposition, CVD, which is pretty standard.
But the nanodroplets, that sounds new.
That's the key. They figured out that incredibly small clusters of platinum atoms, just 1 or 2 nanometers wide, these tiny, tiny clusters actually melt and become liquid droplets at only 120 degrees Celsius.
120 C for platinum. That usually melts at what, over 1700 C?
Exactly. It's mind-bogglingly low, and it's due to a known phenomenon called the Gibbs-Thompson effect. Basically, the smaller the particle, the lower its melting point. It's a nanoscale quirk.
Okay, so they have these tiny liquid platinum droplets at low temperature. What do?
These droplets act like little catalysts, little guides. They steer the growth of single-layer nanoribbons of the amorphous material, in this case, platinum selenide, PT6.
Nanoribbons, like Tiny
Yeah,
strips.
very thin strips. And then this is the cool part. These ribbons naturally merge together, they coalesce, forming a continuous large 2D sheet. Derringer has a nice figure showing this.
So the droplets guide ribbons, and the ribbons fuse into a film.
Right. And the mechanism is fascinating. It's what's called a non-equilibrium kinetic growth. This is vital because normally thermodynamics would favor those 3D clumps. This method kind of overrides that.
How does it do that?
Well, computer simulations showed these liquid PT droplets actually prefer sticking to the edge of the growing PT6 nanoribbon more than they like the underlying surface. They have better wettability on the growing material.
So they stay at the growing edge.
Exactly. They kind of surf along the edge as it grows. And there's more. The droplets jiggle around randomly. That's Brownian motion. When two growing ribbons meet, the droplets at their tips sort of bump into each other. And because of the energetics and this random motion, they tend to make U-turns instead of climbing on top of each other.
Ah, so that prevents multi-layer growth.
Nah.
Clever.
Very clever. It leads to these tadpole-like ribbons that just merge side by side.
And they mentioned self-healing.
Yeah, remarkably, if small holes form in the sheet during growth, the process can actually fill them in naturally. It leads to a really high-quality, uniform film.
That is quite something. And they achieved this at scale.
They did. They successfully grew a 1-inch wafer-scale amorphous PT6 film, only about 1 nanometer thick, incredibly smooth. As far as they know, it's the first time anyone's used CVD to get an amorphous metal chalcogenide this close to a true single layer over such a large area.
Okay, that's a huge step forward in just making the material. So now that they can make it,
Yeah.
what about its properties? What can it do? Let's stick with the PT6 example.
Right, the properties are where it gets really exciting. First off, tunable conductivity. Just by heating the film to different temperatures afterwards and annealing it, they could control the degree of disorder.
Changing the messiness level.
Kind of, yeah. And that directly tuned how well it conducted electricity. They found the lowest conductivity after annealing at 300 degrees C. This matched up with measurements showing the lowest density of available electrons at the key energy level, the Fermi level. It confirms that link between disorder and electronic properties.
Okay, so controllable conductivity. What else?
Second, they measured its work function. That's basically how easily electrons can escape from the material's surface. The amorphous PT6 had a high work function, 4.83 electron volts, EV, significantly higher than standard materials like graphite.
And why is a high work function useful?
It makes it really good for injecting whole positive charge carriers into certain types of transistors, specifically P-type transistors. Think of it as an efficient on-ramp for charge.
And the low growth temperature matters here too, right?
Absolutely critical. Growing these at 120 to 150 degrees C means you could potentially add them onto existing silicon chips late in the manufacturing process without damaging underlying components. That's a big deal for integration.
Okay, tunable conductivity, good for transistors. Anything else stand out?
Oh, yes. Probably the most striking result was its performance as a catalyst for producing hydrogen fuel. They tested for the hydrogen evolution reaction, HER, which is key for splitting water to get clean hydrogen.
And how did it do?
Amazingly well. Unlike typical crystalline catalysts where only the edges are really active, these amorphous PT6 samples showed high catalytic activity across their entire surface edges and the flat basal plane.
So the whole surface works.
The whole surface works.
Yeah.
And the performance numbers were top-notch. They needed very little extra energy and over potential, around 25-30 millivolts, MV, to drive the reaction. And the reaction rate dependence, the Tafel slope, was also excellent, around 43-45 milliVs per decade. That's comparable to pure platinum.
Wow, as good as platinum, but potentially cheaper and using the whole surface area.
Exactly. It suggests the inherent structure of the amorphous material itself is highly active, not just specific edge sites. A direct win from the disorder.
That's huge for clean energy, potentially. And this wasn't just for platinum selenide.
No, they showed the method is versatile. They successfully grew a whole family of similar materials, amorphous noble metal selenides, antimanesses, things like R6, PD6, and RH6. Also came out as ultra-thin, single-layer films between 0.6 and 0.9 nanometers thick.
So it's a platform technology, not just a one-off.
It seems to be, yes. A new way to make a whole class of these amorphous 2D materials.
Okay, let's boil this down. What are the really key takeaways for you listening to this?
I think the first big one is that scientists have genuinely cracked a major problem, making these atom-thin amorphous materials reliably and at scale.
And it wasn't luck.
It was really clever chemical engineering, using basic physics like that Gibbs-Thomson effect in a smart way.
Right, turning what looked like a limitation, the low melting point of nanoparticles, into the core of the solution. Second takeaway for me, This really flips the script on perfect materials. It shows that disorder, when controlled, isn't a flaw. It's a design feature. You can use it to tune conductivity, improve electronic contacts, and dramatically boost catalytic activity, like for hydrogen production. The messiness has function.
Yeah, engineered imperfection leads to superior performance in some cases.
And finally, the growth method itself feels like a big deal for materials science generally. It opens the door to making other non-layered materials in these ultra-thin forms, materials we couldn't really access before, that could unlock applications we haven't even thought of yet.
Definitely. It expands the toolbox significantly. And maybe a final thought to leave you with, if we connect this to the bigger picture. Think about combining this ability to make these tailored, disordered, atom-thin materials reliably, with a growing power of computers to design materials with specific properties before we even go into the lab. Could we soon be designing and building materials atom by atom with exactly the electronic or catalytic properties we need? Imagine custom catalysts for green fuels or new types of computing components built from these designer disorder materials. It really pushes the boundaries of what we might achieve by controlling matter at the nanoscale.
A fascinating prospect indeed. Rethinking perfection at the atomic level. Thank you for joining us on this deep dive into the world of amorphous chalcogenides. Keep exploring, keep questioning. There's always more to discover.